Hello everyone, in this video we are going to discuss about optimizing cryogenic liquid air energy storage with Simulink. It is an efficient grid scale power storage and generation. This simulation model represents a grid scale energy storage systems that utilizes cryogenic liquid air. During the periods of excess power, the system applies a variation of Claude cycle to liquefy ambient air. The resulting cold air is then stored in a low pressure insulated tank until it is needed. When there is a demand power needed, the stored liquid air is expanded to generate power following the principles of Rankine cycle. Let us see the model. Here some small introduction about optimizing cryogenic liquid air energy storage with Simulink. It is a efficient grid scale power storage and generation by using Matlab Simulink. Here liquid air energy storage, that is simply called as LAES, is a type of energy storage technology that uses excess electricity to cool air into a liquid state and store it, and then uses the stored liquid air to generate electricity when demand is high. Sir, LAES typically involves several key steps. The first one is excess electricity is used to power a refrigeration system that cools air into a temperature below its condensation point, causing it to liquefy. The liquid air is then stored in insulated containers or tanks which act as energy reserves. When electricity demand increases, the liquid air is pumped to a high pressure, high temperature environment where it is heated, causing it expand and convert back into a gas. This expanding gas is then used to drive a turbine or piston which generates the electricity. This is the concept of this example. Then by using some optimization algorithm, you can optimize the efficient grid scale power storage and generation by using Matlab Simulink. Then what is liquefaction system? This liquefaction system is the context of liquid air energy storage, is a key component that is responsible for cooling ambient air to a temperature below its condensation point, causing it to transform into a liquid state. The liquefaction process is a crucial step in a LAES cycle that allows for the storage of excess electricity in the form of liquid air, which can be stored and kept until it is needed for energy generation. Here some of the main components in the LAES block. Here first one is the important one is a compressor, heat exchanger and refrigeration system. What is a compressor is? Compressor is used to pressurize the incoming air, increasing its temperature and pressure. The compressed air is then directed to a heat exchanger for further cooling. Then heat exchanger block. The heat exchanger blocks is used to transfer heat from compressed air to a cooling medium, typically a refrigerant, through a process known as heat exchange. The heat exchange process reduces the temperature of the compressed air, causing it to cool down. The third component is a refrigeration system. Already you know very well about this system. Is used to further cool the compressed air to a temperature below its condensation point, causing it to liquefy into liquid air. The refrigeration system typically includes components such as compressor, condenser, evaporator and expansion valve, which works together to cool the air and condense it to in a liquid state. The next process is insulated containers or tanks. The containers or tanks are typically designed to minimize the heat transfer and keep liquid air at a low temperature to prevent it from converting back into a gas. The next component is a control system block. This control system component is used to monitor and regulate the operation of the liquefaction system, including a compressor, heat exchanger, refrigeration system and storage containers or tanks. It ensures the control system ensures the liquefaction process is optimized for efficient and effective energy storage. And the next block is a safety measure blocks. These safety measures such as pressure relief valves and temperature sensors and emergency shutdown systems may also be included in the liquefaction system to ensure safe and reliable operation and to prevent overpressure or overheating. There are important another thing is the pressure enthalpy diagram. It's a graphical representation of the dynamic properties of a substance, specifically its pressure and enthalpy or heat content. It is commonly used in thermodynamic analysis of power cycles such as Claude cycle during the charging process and the Rankine cycle during the discharging process. Then let us see what is Claude cycle, what is Rankine cycle. In the Rankine cycle, which is used during the charging process, the grid scale energy storage system based on the cryogenic liquid air, the pressure enthalpy diagram shows the changes in the pressure and enthalpy of air as it undergoes compression, cooling, liquefaction and storage in the low pressure insulated tank. This diagram typically includes lines representing the compression process, cooling process, liquefaction process and storage process, which shows the changes in the pressure and enthalpy at the each stage of the cycle. On the other hand, the Rankine cycle, which is used during the discharge process in the same system, the pressure enthalpy diagram shows the changes in pressure and enthalpy of the liquid air is undergoes heating, vaporization, expansion through the turbines and condensation, etc. And also this diagram typically includes line representing the heating process, vaporization process, expansion process and condensation process, which shows the changes in pressure and enthalpy at the each stage of the cycle. Then what is the pressure enthalpy diagrams are important tools for understanding and analyzing the thermodynamic performance of the energy storage systems, as they provide visual representations of the changes in pressure and enthalpy that occur during the different processes of Claude and Rankine cycle respectively. Let us see the model. This model has two parts, the charging subsystem and storage subsystem and discharging subsystem. In this charge subsystem, liquefaction and the discharge section is the expansion. This is the energy storage block. Here in the scopes are represent the pH diagram, pH pressure enthalpy diagram of charge cycle during charge cycle and discharge cycle, and you can see the power, storage and efficiency scope here. Here by using this model, we can plot work and liquefaction yield, and also you can plot the charge and discharge cycle. Also you can plot mass flow rates and plot thermal store temperatures, and also by using interactive Simscape result explorer, we can see the simulation result each and every block. Then what are the optimization? How we can going to optimize this grid scale power storage and generation, particularly used for this LAES systems. Here there are several optimization techniques are there, typically involve maximizing the performance or efficiency of the grid scale energy storage system based on cryogenic liquid air, particularly during the charging and discharging process of Claude and Rankine cycle respectively. There are some common optimization algorithms are used in energy systems optimizations. This can be achieved by carefully controlling various parameters or variables that affect the system performance, such as compressor speed, expander speed, pump speed, heat exchanger design and operating temperature. Now let us see what are the different types of optimization algorithms used in energy systems optimization. First one is a gradient based method, second one is genetic algorithms, third one is particle swarm optimization, and the next one is simulated annealing and Nelder-Mead method, genetic programming and sequential quadratic programming, etc. Let us see one by one. What is the gradient based methods? These algorithms such as gradient descent or Newton method use the gradient or derivative of the object function with respect to the variable to iteratively update the variables towards the optimal solution. Then next one is a genetic algorithm. These algorithms inspired by the process of natural selection use genetic operators such as mutation, crossover and selection to evolve the population of candidate solutions towards the optimized solution. Third one is the particle swarm optimization. In this algorithm models the behavior of swarm particles that move through the solution space to search for the optimal solution based on their positions and velocities. Next one is a simulated annealing. This is based on the concept of annealing in metallurgy, where a material is heated and slowly cooled to reduce its defects. It uses probabilistic approach to search for the optimal solution by allowing occasional uphill moves to escape local optima. Next one is a Nelder-Mead method. This algorithm constructs a simplex geometric shape with n+1 vertices and n-dimensional space, and also iteratively moves and reflects the simplex to search for the optimal solution. Next one is the genetic programming. It is a tree-based representation of candidate solutions and evolves the trees through genetic operators to find out the optimal solution. And the last one is the sequential quadratic programming. This also a numerical optimization technique that uses the quadratic approximation of the objective functions and constraints to iteratively update the variables towards the optimal solution. Now let us see the gradient. You can see with gradient descent optimization algorithm for this model, efficient grid scale, power storage and generation. Then what is gradient descent optimization? It's a popular optimization algorithm used in many applications including energy systems optimization. It is a method iteratively updates the value of decision variables to minimize the maximize and objective functions. In the context of optimizing performance of grid scale energy storage system based on cryogenic liquid air, gradient descent could be used to iteratively update the values of decision variables such as pressure enthalpy of the working fluid during charging and discharging process of the Claude and Rankine cycles. The objective function could be defined based on the desired performance objectives such as maximizing the net power production or minimizing the energy consumption. The gradient of objective function could be computed using the derivatives of relevant thermodynamic equations or simulation models. Then finally, by updating the decision variables based on the gradient, the algorithm would converge towards the optimal values of decision variables that optimize the performance of the energy storage system. Then this slide shows simulation result from scope and simscape logging, especially for power efficiency and energy storage. This scope shows the net power consumed the liquefy air during the charge cycle and the net power produced from the stored liquid air during the discharge cycle. About 10 megawatts is consumed during the charge and 1.8 megawatts is produced during the discharge. This is the second one. The charge and discharge phases run for 10 hours each, allowing the system to store about 15 megawatts per hour energy calculated based on the enthalpy difference between atmospheric air and liquid air. The third one is the time average efficiency of the charge cycle is about 26% and the discharge cycle is about 56%, and finally the round trip efficiency is about 15%. This slide shows the mass flow rates of air, heat flow into thermal store and energy storage. In the left plot, figure the mass flow rates of air through the key components in the systems are shown. During the charge cycle, the compressor drives approximately 27 kg per speed of air through the liquefaction system. More than 70% of compressed air is diverted through the expander to recover some of the work and improve cycle efficiency. During the discharge cycle, the pump consumes 7.5 kilograms speed of liquid air from the tank to run the turbines or generating power. The right hand side plot, it shows the approximately 150 metric tons of liquid air is produced and stored in the tank, corresponding is about 15 megawatts per hour energy storage as seen in the scope. Then finally, the pressure enthalpy diagram is also available in simulation result SimScape logging. The pressure enthalpy diagram already we discussed, graphical representation of thermodynamic properties of substance, specifically pressure and enthalpy diagram. This diagram shows Claude cycle during the charging process. What is a Claude cycle? Which is used to during the charging process in the grid scale energy storage based on cryogenic layer. Also, this diagram typically includes a line representing the compression process and cooling process, liquefaction process and storage process, which shows the changes in pressure and enthalpy at each stage of the cycle. Is a charging during charging process. Is a next diagram shows the during discharging process. In the Rankine cycle, which is used during the discharging process in the same system, the pressure enthalpy diagram shows the changes in the pressure and the enthalpy of the liquid air is undergoes heating, vaporization, the expansion through the turbines and condensation. This diagram includes the line representing the heating process, vaporization process, expansion process and condensation process. Now let us see the model. Now see, these are Matlab Simulink model available in our MathWorks website. This block shows 3 different blocks. That's a charge block. That is liquefaction blocks. This is an energy storage system. These are discharge blocks. Here discharge blocks are having evaporator, and these were expander liquefaction having cooler and expander and compressor. Each of the blocks are available in SimScape fluid subsystem. Just you can drag and drop and draw this one. Then what are the inputs are you are going to given means these are charge and discharge cycles in form of signal builder. You can give the values. Otherwise, you can see the pulse type, time based or amplitude, period, all the things you can give here. These are charge and discharge and pressure, thermal heat and all. The next one is a diagram charge cycle pH diagram and discharge cycle pH diagram. This scope shows power storage efficiency. Now we can see the plot work and liquefaction yield. This is output for energy storage. Next one, plot power for charge and discharge and next one is the part power for mass flow rates, and next one the thermal storage of temperature, and finally by using Simscape result explorer you can see the result as each and every point. Now you can see in this from the left panel we can select the signal to display the plot in right hand side. Now we can set there are several blocks are there. First one is the air inlet, air outlet, chiller block, cold thermal store. And you can see which each and every block what is the plot for this compressor and all. There is a absolute difference mass energy flow rate. It takes some more time to respond it. Now in this way you can see each and every block you can get the output of the particular block. This is an interactive application of this Simscape result explorer, this one. Okay. Finally you can see by using the scope you can see the output for energy stored and average efficiency and net power consumption or production in terms of milliwatts. It is a pH diagram for charging and discharging cycle. These are charge one, and next one is the discharge one. Now we can see the output for charging and discharging. You can see I hope you enjoy this video for this optimization for especially for energy storage system. You can see it takes some more time for running this one. It's cycle the 3 complete cycle, so that it takes some more time. Now we can see the result. You can see the movement of charging and discharging. Now we can see this discharge cycle and charging cycle output. It start from beginning. There are three different cycle temperatures are there. First one is a zero diagram. Now we can see these are charging period. Now also you can see the discharging period. This is a pressure enthalpy diagram, shows this line pressure versus specific enthalpy for this cryogenic liquid. Now you can see after charge cycle, you can see there's some difference. This is discharge cycle is moving on. Now you can see the output for net power consumption or production charge during the charge and discharge. Energy stored also showing here. Both charge cycle of this pH diagram showing now, and also the scope shows the net power consumption and energy stored in this critical system, and also you can see the average efficiency during charge cycle, during discharge cycle, and also this orange color line shows the round trip efficiency. Okay, I hope you enjoy this video. In this model available in my YouTube channel description box. Kindly download it for research and study purpose. Thanks for watching. If you are new viewer of my channel, means kindly subscribe my channel and like, share to this model to your friends and students, and also kindly give a like and give some worthy comments on my YouTube channel videos. Thanks for watching. Thank you.